Hello everyone, welcome back to Simscope. Have you ever wondered how to convert a low DC voltage into a stable higher output without a noisy current ripple? In this video, I am going to show you how to design a Cook converter from scratch in a MATLAB Simulink, including all the real engineering calculations, not just tracking the uh, Simulink blocks and functions. And by the end, you will also understand how to get a stable 25-volt output from a varying input between 15 volt to 35 volt. So, firstly, I'll take you through the what is a Cook converter. Cook converter is a non-isolated. It is a DC to DC converter that can either step up or step down the magnitude of a DC voltage. That is a Cook converter, and in our project here we we are giving an input voltage of 15 volt to 35 volt, and our output voltage should be 25. That means we are increasing. If we are giving the input of 15 volt, then we are increasing our output voltage to 25 volt. If we are giving an input as 35 volt, then we are decreasing the output voltage to 25 volt. So that is what we wanted to see by doing this project, and the output ripple should be just 2%, which is peak to peak. Then switching frequency for the converter is 100 kilohertz. As per the question, it is also given that the load range should be 100 watt to 500 watt, and controller can be open loop. You can use the semiconductor modeling, non-ideal transistor, on state drop and diode forward. That means we are allowed to use a we are not allowed to use ideal components. So this is like a real world design. Now moving on to the conceptual explanations about the Cook converter. It is sometimes called as a buck boost converter, or it can be boost buck converter too. But mm, in the buck boost converter, the Cook converter is like a buck boost type converter, but with a twist. Instead of transferring energy uh, directly through the inductor, it uses the capacitor as a energy transfer element here. And also very important, the output voltage gets inverted here. So when we say 25 volt, it actually uh, gives you negative 25 volt with respect to the input ground, or whatever we give as input. So this converter has two inductors, inductor 1, inductor 2, L1 and L2, and they will smooth the current. The capacitor 1 is a transfer energy transfer element. Then it uses one switch. It can be IGBT or transistors, and another one, this can be IGBT or MOSFET, I mean. And it do have one freewheeling diode placed something like this, and I'm using the capacitor C0 to filter the voltage at the output. Okay, that is the topology. And what happens? It contains Cook converter contains two inductor, one active switch and diode, and an energy transfer through capacitor. Energy is transferred from input side to the output side using the capacitor. And because the way the capacitor and diodes are arranged, the output polarity is reversed. So this is very important. Now what happens when the switch is turned on? The inductor L1 stores the energy, and energy from the source. The diode is reverse biased, and the transfer capacitor C1 delivers energy towards the output side, while the output inductor L2 continues to supply the load current. Now when the switch is off, the diode becomes forward biased, and an energy stored in L1 and the transfer capacitor is transferred to the output side. The output inductor smooths the current supplied to the load, and if both the inductor current remains above zero for all operating points, the converter is operating in a continuous conduction mode. Okay, now for uh, the equations that we are going to use, we have V output divided by V input. Output voltage divided by input voltage is equals to negative of duty cycle divided by 1 minus duty cycle. That is the equation that we're going to use, and the output voltage can be given by this equation, and the polarity does not really matter here. We have to ignore it if it is negative. Then we want to calculate the duty cycle. To do that, we are just bringing the d out, which makes you output voltage divided by output voltage plus input voltage. And since the assignment requires non-ideal semiconductor behavior, the practical voltage drops are approximately, we are setting 0.2, but the diode will have 0.7 volt, and after rearranging we get the duty cycle something like this. Now the load calculation, we have 100 watt to 500 watt. We want our load to be in the resistance. Instead of, we are going to simplify the load and not going to use the load um, function. Instead we will use a series resistor as a load. Therefore we will convert the resistors by using this formula. Resistor is equals to V square divided by power, and for 100 watt power, if we give a minimum of 25 volt, then the resistance load should be 6.25 ohm, and for the maximum load of 500 watt, again 25 voltage of 25 volt square divided by 500, it gives you 1.25 ohm. So that means the maximum load at 100 watt, it is, the resistance is 6.25. At maximum load of 500 watt, the minimum is 1.25 ohms. Therefore, now if we calculate the output current range, then we are getting 4 amps for minimum, and output current maximum we are getting is 20 amps. Now calculating the duty cycle. At V in of 15, the duty cycle is 0.625, 25.5, 35, then the duty cycle is 0.416. That is the duty cycle we are going to use. Oh, that is in the ideal duty cycle. Now we have to also consider the duty cycle including the non idealistics with with the non-behavior voltage drop, considering the behave non-ideal voltage drop behavior of the diode and the switch. So using that, we are getting at input voltage of 15 volt, we are getting the duty cycle of 0.6346. At 35 volt, the duty cycle is 0.4248. Using this duty cycle, we can then fix the output into 25 volt. Now, to calculate the inductor values are selected, and to keep the current ripple moderate, we have to ensure it is CCM, continuous conduction mode, over the entire operating range. Therefore, L1 can be approximately 56 microhenry to L2 of 56 microhenry. The input inductor ripple, now we calculate here. I'm not going to go in detail. Capacitor designs, capacitor calculations here, then the filter capacitor designs here, then after calculating, we are considering some values here, and semiconductor stress and practical ratings are used. Finally, we have the output here. In the MATLAB block, this is how we can use in the MATLAB. Okay, these are the calculations. Now we just go and put these values into the inductor. Like inductor value is 56 microfarad, then again 56 microfarad. The capacitor one is 220 microfarad. The filter is 220 microfarad. Now we have the input voltage of 35. So at 35, if we're giving it 35 volt, our load should be this is a current, our load resistance. So I already have 6.25 ohms load. The output voltage will be given by this display block. Output current is given by this output current. Then the voltage across the inductor is given to the scope here. Then we can get the output power just multiplying the output voltage times output current. And for the pulse that is going to switch the IGBT here, we are giving a gate pulse from comparing the repeating sequence of sawtooth values with
the duty cycle, we're saying that when the duty cycle is 0.425 and the time value here is calculated based on the kilohertz or the switching frequency we wanted. So this is the pulse generator, and at the output we are getting a pulse. This pulse is given at the gate of the IGBT. When the pulse is high, the IGBT will switch on. When the pulse is low, the IGBT will be switched off. And by switching on and switching off this IGBT, we are making the converter to either uh, decrease or increase the input voltage to a constant voltage of 25 volt. Okay, let us simulate once and see what happens. Okay, the duty cycle should be 0.25. We are doing the simulation test of this one, and case 3, 35 volt, 100 watt, 6.25 ohm, 0.425 duty cycle. And let's see what happens at the output. Okay, we got an output of 25.32 volt. Again, remember that this converter always gives you voltage in the your polarity is reversed, right? Now simulation says that your input is 35 volt and your output is 25 volt when the load is 100 watt. Now let's try 15 volt, the minimum input voltage. The input is 15 volt, then power is 100 watts, so the load will remain same as 6.25 and the duty cycle should be 0.635. 0.635. And our load is 6.25. Okay, let's simulate. Now even if your input voltage is changed, the output you are getting from the converter is still 25.42. I have a scope here comparing the waveforms. First waveform shows the output voltage. The second waveform is showing an inductor voltage. Then gate pulse is given. Then finally the output current is shown here. So if we just go around somewhere here at the steady state and see the voltage, now you can see that your output voltage is minus 25, right? Now you can see that your switch is turned on here and turned off here. It becomes negative, it becomes positive. So, oh, sorry, this is a conductor. I mean the inductor voltage. Your inductor voltage is approximately around 18 and minus around 18 volt to minus 23 volt. Now your gate pulse is here. You can see that When the gate pulse is off, your inductor is getting charged. When it is conducting, when your switch is turned on, your you have a high inductor voltage. When you have a switch off, the inductor voltage is decreasing and reduced to the negative. That means it's drawing the output is drawing the inductor from the source. This is a source inductor L1. Now the current is approximately -4. That is the waveform here. We are saying that using a repeating sequence here at the PWM generation, our time is 0 to 1 e to the power -5, and it should output the output value of 0 and 1. This is compared to the duty cycle so that it can generate a pulse. And our simulation is simulated in a discrete with a power Q put in the discrete with the sample time of 1 e to the power -7. Now when we check the output voltage, we are getting 25 volt. The ripple is less than 0.5 volt. You can see that the inductor current never reaches to zero. It never reaches to zero. So it is either positive or negative. Therefore, we can say that inductor is in the continuous current mode operation. So if they stays above zero, we can say that the design is correct. One important observation is input voltage increases. We can see here that when the input voltage increases from 15 volt to 35 volt, the duty cycle is decreasing, right? Duty cycle is decreasing. This is exactly how the Cook converter maintains a constant output voltage. And also using a large capacitor significantly reduces ripple, which is critical in a high power application. So that's a complete Cook converter design from equation to simulation. If you want the full simulation model and report, please check the link below. And if you are serious about mastering power electronics and MATLAB simulation, subscribe to Simscope. See you in the next one. Thank you.